All right, so we are back with the second lecture on the atmosphere. Last time I said we would get into the different layers of the atmosphere and talk about how that's related to things like the ozone in the atmosphere and also to just the absorption of solar radiation in the atmosphere. So your book talks briefly about the three different ways that heat is transferred and kind of describes how all of those are related to the atmosphere. So conduction is when something is actually touching something else and it passes that heat into it, and that works by a process kind of like a diffusion of heat where the very energetic, hot molecules strike up against the less energetic, cooler molecules and therefore speed them up, just like when you take a pool cue and you use the high speed of that to strike a pool ball, right? Uh, that's a random process, but it happens through contact. Conduction, that was conduction. Convection, we've already talked about before with like the convection of, um, I think we use it for momentum convection, but the basic idea is anytime a substance like a water or something like that is bringing heat with it. As it flows, that heat is moving by convection. Air, of course, is the same way. Air that's warm, that moves from place to place, is moving that heat with it, and therefore will bring convective heat into that area. That's definitely important for climate and weather that we'll talk about later on. The last type is radiation, and radiation is where there's actually an emission of uh, light energy of some kind, something along the electromagnetic spectrum. Often we're thinking with heat on Earth, because Earth is the blue planet, we have so much water, we're usually thinking of an infrared type wave. It could be any kind of wave, and the hotter something is, the higher energy wavelengths it can put off. That's right. I mean, that's why when something is really, really hot, we can say it like glows, it's white hot or it's red hot, because it will start to give off visual light in that case, which is higher energy than the infrared. But in general, we are usually thinking infrared when we think of thermal radiation. Of course, as we said, any radiation can create heat, though, or carry heat. And so ultraviolet is going to be very important in atmospheric heat distribution, especially in the stratosphere. With that out of the way, I just wanted to mention that because that is part of that chapter 11 reading that I hope you're doing. Uh, but to talk about the layers of the atmosphere using that, the first thing to notice is, well, when we look up in the sky, there's no walls kind of separating the different layers of the atmosphere, right? So there must be some other way to define a layer within it. And if we look at this graph, which has altitude on the y-axis and temperature on the x-axis, this is a rare example of a graph where the dependent variable is on the x-axis, and that's just because altitude looks weird to put that on the horizontal, right? If we had this correct where the independent variable was on the x-axis, it would be a very weird looking graph. So instead we put that on the y-axis and we have temperature, and in the troposphere, the temperature is decreasing with height. So as we get higher, it gets colder. And then in the stratosphere above the tropopause, so the pauses separate the spheres, remember. So the tropopause here separates the troposphere from the stratosphere. In the stratosphere, it's getting warmer again as we get up higher. And then in the mesosphere, it gets colder again. Thermosphere, it gets warmer again. And exosphere, there's, again, just like we talked about in the first quarter, temperature stops being kind of meaningful because there's so little material that, if you went up there, it would feel simultaneously cold and hot. Just because there's not enough material to actually vibrate against your skin, making it feel cold, but it's also, you're being blasted by solar radiation, so it's very warm. But in any case, let's talk about these different levels. So the troposphere Again, it's warmer on the bottom, and that's because a lot of that energy that passes right through the atmosphere, the radiation that is not absorbed by the atmosphere. So here we're thinking visual light, we're thinking uh, infrared light, right? We're thinking um, some amount of things like X-ray and radio waves even that get absorbed by the water or the surface greenery here, that right visual light is absorbed by green plants, red and blue light is, excuse me. So all of that's going to warm up the surface compared to these higher areas here. And as the surface is quite warm compared to the atmosphere, it will conduct, and to a certain extent convect, but it will conduct heat upwards away from that surface to where the surface is the warm thing. The lower atmosphere here in the troposphere is the cold thing. Note that this isn't to scale, by the way. This is a logarithmic scale. So this is 10 kilometers up, and this is 100, right? That's not a linear scale here. But here at the troposphere, it's going to reach kind of a coldest point in the tropopause, at least compared to the surrounding areas. And then it's going to start to warm up again. And that is very peculiar, right? Why is it suddenly getting warmer when it doesn't seem like there's anything absorbing the energy there, right? That's what makes something warm, is something absorbing solar energy in the form of radiation. But actually there is what is not shown here. Well, I lied. It's shown right here. Is the ozone layer. So the ozone layer, again, ozone is 3 oxygens. It's a more unstable form of oxygen than oxygen gas, O2, and it absorbs that ultraviolet light. The ozone turns back into oxygen. Oxygen also absorbs ultraviolet light, turning back into ozone. So here, there's just this like massive amount of absorption of ultraviolet, especially radiation. That is going to conduct downward and conduct and convect upward because hot air rises, right? Because it's less dense. So that hot air rises, convecting some of that heat up above the ozone layer, and it conducts in both directions, making kind of this coldest point below the ozone layer, the tropopause, and then a warmest point above the ozone layer called the stratopause. And then at some point, the heat from that ozone layer starts to dissipate again, and we get to actually the coldest point in the atmosphere overall, the mesopause at the top of the mesosphere. So in the mesosphere, we're kind of seeing that, yes, Sophie, we're seeing that energy from the ozone layer being absorbed and kind of running out of heat as it moves up higher. And as we get far enough away from the ozone layer, in the mesosphere, it gets very cold again, and the mesopause is the coldest point in the atmosphere, and actually the coldest point on Earth, if you think about it, because we all know that the geothermal gradient means that deep underground, it actually starts to get very hot. And if this is the coldest point above the surface, then it makes sense it would be the coldest place on Earth. And we're talking down in the, what's that, almost minus 90-ish, minus 100 degrees Celsius position. And then above the mesopause, in the thermosphere, there is again an increase there. Again, that's where there's going to be an increased amount of absorption of solar radiation, because this is where all the different kinds of radiation that don't even make it down to the ozone layer are initially absorbed. So every particle, even though there's much fewer particles up here in the thermosphere, this is just missing an S. That's a typo. Even though the thermosphere has fewer particles, just as the mesosphere has fewer than the stratosphere, and stratosphere has fewer than the troposphere, each particle has a lot of energy, so it's a high temperature. And it actually gets to outrageously high temperatures up here in the thermosphere. But again, that's not really as meaningful as the temperature in the center of the Earth, just because that temperature is averaged over very few particles. Again, to kind of go over each layer, the slideshow does a good job of this. I'm not going to necessarily read everything here. Just I encourage you to do so, though. The troposphere is definitely the densest part of the atmosphere. It has 90% of the mass, even though it's just a small fraction, if we go back, of the actual thickness. Kind of like 1% if we include the exosphere here. So highly dense compared to other areas of the atmosphere. It's where all weather occurs. It's where all clouds occur. If you're flying in a plane, you're probably flying at the top of the troposphere. There's not going to be much turbulence because all the weather's below you, right? So if you're wanting to avoid turbulence, you go up higher than the weather. And if we go up above the troposphere, up to the tropopause, that weather doesn't affect us. As it says, the temperature is quite cold at the tropopause, about minus 50 C, but that is not the coldest part on Earth. Commercial airlines, as this says, you fly above the troposphere in order to avoid issues with rising gas and weather and things like that. Stratosphere, we already talked about the ozone layer. This is a good video if you want to watch it. You can click that link on your own slideshow. It's just basically a guy jumping from the stratosphere, and you can clearly see the Earth is round. So, all you flat earthers, check that one out. Mesosphere, again, this is where we are starting to lose out on that energy from the ozone layer. The coldest place on Earth is the mesopause. I would know that. That's like a fun fact to know for a quiz or a test, huh? And then thermosphere, it is the thickest of the layers. This is biggest, obviously not by mass. As we said, the troposphere is 90% of the mass. The air would therefore be very thin just because there's low density, but it also has lower oxygen. If you look at the oxygen molecular weight compared to that of nitrogen gas, right? Oxygen's heavier by what? Well, nitrogen is 28 units of molecular weight, and excuse me, I think I said that right. Nitrogen is 28, 14 times 2, and oxygen is 16 times 2, 32 molecular weight. So the oxygen will preferentially sink to the bottom, right, compared to the top. So the fraction of oxygen is also higher down here in the troposphere. And that just has to do with density and mixtures, as we've talked about plenty of times. It keeps coming back in our science how denser things sink, right? And then, sorry, that's my phone ringing. I'm just going to let it ring. The ionosphere, it's not sitting next to me. I would turn it off. But the ionosphere here is within the thermosphere. And we will talk about that more with weather probably. But basically, this is an interaction between solar radiation and the atmosphere that will basically the ions, or excuse me, the molecules, there we go, finally. The molecules that have absorbed that radiation, their electrons get shed out, kind of like a plasma. So the ionosphere is kind of plasma-like and has times when there's lots of plasma in the ionosphere, and that is visible to us as the aurora borealis and the aurora australis. The northern and southern lights. That's basically where, again, the solar radiation is coming in at a certain angle, creating these streams of plasma in the ionosphere. Oh, well, I always just remember to talk about things right before the slide comes up. You can look at those there. Exosphere, again, really is nothing. It's hard to even call it gas at that point. It's so not dense, but it's still much more dense than the interplanetary space, or the kind of the dust between stars in a nebula, for example. And it's very possible for gas molecules, especially lighter ones like hydrogen and helium, to escape from Earth and leave the planet up here. That's just a good picture of what's called the geocorona, this part right here. This is the actual atmosphere. This is the geocorona. As far as the magnetosphere, we will talk about that probably not in another lecture here, but go ahead and read through the rest of these anyway. Here we talk about these radiation, conduction, convection. I will probably not make a lecture over this material, but you are responsible for it, so go ahead and look over it. Here, air temperature and pressure is where we might pick up on the next one. All right, thank you, gentlemen. Until next time.